When we discuss about the seismic stratigraphy, we deal with the reflection data, and by the seismic reflection data we try to find out the variation in the acoustic properties of rocks, and this can be picked up by generating first of all artificial shock waves and then record its returning waves. Here sound waves or the sonic velocities can be studied. Acoustic impedance is important, and it involves two important terms, density and the sonic velocity of the material. Sonic velocity matters because generally the crystalline or well cemented rocks have higher sonic velocity, higher than the clay rich or the porous rocks. More porous a rock is, lower is the sonic velocity. From this point a seismic wave can be sent and it gets reflected on this plane and comes back. Time required to go here and then come back combinedly is called the two-way time, and from this two-way time the depth of reflector can be obtained. The depth d can be obtained. Signal generated by each reflection are merged, and this process is known as stacking. Now, the seismic image that is obtained is not free from geometric distortion. So, the angular relationships what is observed there need not be the actual one. Let us look at the different reflection pattern, continuous reflection, and we can compare with this figure. A well defined reflector marks a boundary between two layers of different acoustic impedance, and for this to be continuous over kilometers, it must mark a change in lithological characteristics of the same extent. The continuous reflectors can mark significant widespread change in deposition within the basin. For example, continuous reflectors can mark significant widespread change in the basin. For example, the sea level change may cause sandy shallow water deposits to be replaced by muddy deeper water sediments. Suppose sandy shallow water deposit is vertically followed by deep water muddy deposit, then their contact can act as a continuous reflector. Therefore, these prominent reflectors are considered to represent timelines. So, these lines can actually represent the timeline synchronous event over a large extent. What are clinoforms? Inclined surface bounding stratal packages of seismic reflection profiles are referred to as clinoforms. It is here and they are inclined. So, in this portion we are talking about. They form a pattern that indicates a progradational geometry of packages of sediment building out into the deeper water. As I said that there are angular distortions in the seismic images. The angle of the clinoform seen on the seismic reflection profile may not always represent the true depositional geometry, and the angle may be enhanced by compaction in some instances. If I draw a line parallel to this line here and say this is the clinoform and say this is the horizontal surface, this angle theta need not be the dip of the plane. If we can identify the reflector termination, then unconformities can be identified. Here we find a relationship of reflector termination. These are getting terminated over the line AB. So, this AB line can be called an unconformity. We will discuss separately onlap, which has been referred here. The same figure is presented here. Let us look at the erosional truncation. Here is an erosional truncation. Here a surface of truncation is at high angle to the orientation of the layers it intersects. In this portion, this plane is of high angle. What can be the reason of their formation? There can be subaerial or submarine erosion, and that is why this is an erosional surface. The word erosion comes here. There can be another reason of truncation surface. When the incision of a river valley happens, then such surfaces can be produced. On lap, there can be a time gap between deposition of two units, say one is here and another is there, and such contact does not persist for a very long distance, then these contacts are known as the onlaps. Onlap is an example of unconformity. Onlap is a kind of unconformity. Let us take downlap, which is presented here. Downlap is a contact between the lower horizontal surfaces and upper angular reflectors. This is called as the downlap. Inclined surfaces that terminate downwards against a horizontal surface, and such features are rarely seen in smaller scale of outcrop, can be more found in the seismic images. These are the places where the coverage is many kilometers, whereas in outcrop or observation can be few meters, and in few meters such a relationship may not be possible to find out. Let us look at top lap. Here is the term top lap. In case of a top lap, the upper layers are horizontal and the inclined reflectors can be found at the bottom. So, this one is called as a top lap, and in one way top laps layers disposition above and bottom is completely opposite to down laps disposition of layers at the bottom and the top. Off lap, it refers to a pattern of reflectors rather than a reflector termination. Off lap is a pattern of stratal package that builds upward and outward into the basin. Let us look at a few typical seismic reflection patterns: parallel pattern, subparallel pattern, divergent pattern, in parallel, parallel and wavy, disrupted pattern, contorted pattern. These are the examples of chaotic pattern. In the clinoform, this is the sigmoid variety, this is the oblique variety, and this is the parallel variety. This is a complex sigmoid oblique variety, this is the shingled variety, and this is the hammocky clinoform. The sigmoid clinoforms tend to have low depositional dip, typically less than 1 degree, whereas the oblique clinoforms have depositional dip up to 10 degree. The hammocky clinoforms consists of irregular discontinuous subparallel reflection segments forming a practically random hammocky pattern marked by non-systematic reflection terminations and splits. The shingle clinoform pattern typically reflects offlapping sediment bodies on the continental shelf. If we look at onlap, downlap, truncation and top lap in separate figures, these are the examples. In case of onlap and downlap, these are the examples of terminations above a surface, and the examples of terminations below a surface are the truncation and top lap. Note here, truncation word and termination word should not be confused. Truncation is a kind of termination as per this terminology. The stratal geometry associated with prograding shelf slope system can be of two types: sigmoid progradation and oblique progradation. In case of a sigmoid progradation, we do not see the curve getting terminated any line, rather it is continuing, whereas in case of oblique progradation we find that these lines are tangentially terminating actually across a common line. What is stated for this also holds true for the bottom line. The seismic phases units can state may be presented: continuous low frequency, low medium amplitude, continuous low frequency, medium high amplitude, continuous high frequency, high amplitude, then discontinuous high frequency, high amplitude, and the chaotic phases. The hammocky seismic phases, characterized by short, curved and discontinuous reflections, is presented here. The hammocky one was described in the context of clinoform in this case. How the reflections terminate: if they terminate at the upper boundary, it can be erosional truncation, top lap or concordance, and here we do not see a cut relationship, and if it is a lower boundary, it is on lap and down lap, and again concordance. The issue of upper and lower boundaries truncation was also described with these diagrams, presenting same thing in a different way. The erosional truncation, the top lap, the concordance with subtle indications of sediment bypass are presented here. Examples of down lap presented here, and these are the examples of the on lap. These are the uninterpreted images and these are the interpreted images. This is an example of submarine canyon on the seismic data. You can look at atlas of seismic image interpretation and few books will be available on this broad topic. Further, on the seismic facies types on the shelf, high amplitude and continuity interbedded high and low energy is reflected here. Low amplitude indicating uniform energy is demonstrated here. Low continuity and of variable amplitude indicating variable energy is represented here. Broad low relief mound and variable amplitude and continuity indicating variable energy condition can be represented in this diagram. The different types of force sets, oblique progradational or high energy condition can be revealed, or it can be sigmoid progradational indicating a low energy condition. So, here what happens, these lines are not terminated against any line, rather they are continuing in a sigmoidal manner, whereas here these lines are actually terminated. This is an example of salt diapir and how it appears in the seismic image. The platform carbonate buildup is shown in terms of uninterpreted image and the interpreted image. The external geometries of seismic facies units on the slope and basin floor. Some examples: sheet drape indicating low energy condition, slope front fill indicating low energy condition. This is a slope. On lap fill, this is the depression where low energy condition is indicated by such a situation. Fan complex, from high altitude rivers came and were flowing. Suppose you made a cut, or in other words you are looking at a seismic section, then this kind of pattern can be found indicating high energy condition. Mounded on lap fill indicating high energy condition would be reflected by this kind of seismic profile shown within this portion. The chaotic fill can be found where we do not see pattern in this vertical section and also in that vertical section. The external geometries displayed by the mound types: fan complex, and it is simple. Slump geometry, this is the place of this slump where we do not see any pattern within this portion. Haphazardly oriented materials will be there. Fan complex and compound geometry. Volcanic mound would have this kind of seismic reflection profile. Amongst the carbonate mounds, pinnacle with velocity pull up, this is a homogeneous with drape, this is the drape. Bank edge with velocity sag is here, and several other varieties are there. Reflection patterns within fill, this is on lap fill, this is prograded fill, this is mounded on lap fill, this is the chaotic fill, this is the divergent fill, this is the complex fill pattern. In chaotic fill, we do not see any specific orientation of the seismic reflections. We will see petrophysical logging. In a previous lecture, I have already covered image logs. Interested students can have a look at that, and here I am going to cover the gamma ray log and the sonic log. Suppose through gamma ray log we are observing sedimentary succession, and sonic log, using that we are also looking at the sedimentary succession. A high value of gamma ray log, natural gamma radioactivity, indicates higher potassium content. So, whenever we have got the high value, high potassium content has been marked, and high potassium content can be found within the shell or in feldspathic or micaceous sand. So, these are the interpreted rock names. In case of coal also, the potassium content can go very high. In case of bituminous shale also, the potassium component can go very high. So, there is a peak over here. For coal and limestone, the potassium content goes low. So, it is a bell pattern. For sand, it is low, and for mixture of sand and shale, the amount is in between that for pure sand and that for pure shale. So, this is for the mixture of sand and shale. Let us take the example of sonic log. Sonic log gives us an idea about the density of the rock. Since coal has a low density, the interval transit time for coal is low and it is variable because coal is heterogeneous material. Since compact sandstone has more density than porous sandstone, there is a peak here and then there is a progressive fall. Since compact limestone has higher density than that of the porous limestone, therefore, this difference can be seen. If there is a rock A with two varieties, porous, another is non-porous or compact, then sonic log shows a peak here and here it will show a fall. But from gamma ray log and sonic log, or for that matter any geophysical log, pinpointing exact rock type is not always possible. So, the other lines of evidences of what can be the rock type has also to be looked at. Now, we are going to look at gamma ray traces depth wise. In all these graphs, this is the z direction vertically downward. If we are in a sedimentary terrain and we have narrowed down the rock types, then for such a pattern we say that this graph represents alternating sand and shale beds. For shale, the natural gamma radioactivity is high due to high potassium content, and here as we see fluctuations, this means that there must be high potassium content and low potassium content material, and if it is a sedimentary terrain, we reasonably guess it can be alternating sand and shale beds. So, what can be the interpretation here? Here we are getting two peaks of high potassium content. So, overall we think that there are thick sand bodies and in between there are thin shale units. So, it is a sand with thin shale bodies, and conversely if this is the situation, then here are the lows of gamma rays. So, this can be sand, whereas these regions can be shale. So, the interpretation here goes like this: is a shale with thin sand bodies if we are dealing with sedimentary rocks. In what way the geophysical log can be linked with the sequence stratigraphy? Consider this is the location of drilling, and we will see progradational parasequence, retrogradational parasequence and aggradational parasequence. We are having three kinds of rock types: shelf mudstones, shallow marine sandstones and coastal and plain sandstones and mudstones. 1, 2, 3, 4 numbers inside the circles in these three cases represent the individual parasequences. So, if a drilling is done here, this is the zone we get one kind of log response. Here is a different kinds of rock types, so we get some pattern. Here is a change in rock types, and then again here is this rock coming back, and then this rock type comes back here. Let us look at the log responses. SP log in the left hand side and the resistivity log in the right hand side, and the patterns can be seen. These rock types have been interpreted and accordingly the color has been inserted. Depending on the geophysical parameters in the shelf mudstone, shallow marine sandstones and coastal plain sandstones, the curves show this kind of variations. When we are looking at the resistivity log from the shallow marine sandstones here into the shelf mudstone here, and then again into the shallow marine sandstone here, let us consider this boundary. So, here we have got the shelf mudstone and here we have coastal plain sandstones and mudstones. And what do we observe in the resistivity curve? From here the curve takes a jump. Similarly, you can look at this jump and correlate, and look at this jump and correlate. Similar observations can be made with the SP log and resistivity log in case of aggradational parasequence and the progradational parasequence.